Okay, so getting into the thick of it here. Radiative transfer in the ocean. You saw a similar slide from Darius, but this kind of summarizes the processes where you have this beam of light, this pencil of light, represented by radiance or L, and that goes through an elemental volume. There's some losses due to scattering. There's some losses due to absorption. As Zhongping mentioned, those are the two processes by which light is altered as it transfers through a medium. But there can also be gain from scattering as well. So the inherent optical properties, as Zhongping stated, are dependent only on the substances in the water. These are properties of attenuation, absorption, and scattering. Absorption plus scattering, A plus B equals C. You guys know that. And then apparent optical properties dependent on the IOPs, but also on the ambient light field. And I think probably David Antoine is going to talk about that in more detail later. So obviously the focus here is the scattering. So is the volume scattering function defined? So it was interesting. This is a definition. It's a little different from Zhongping's. Use grading coordinates, but it's the change in light intensity as a function of angle, and that's normalized to the incident irradiance, E, of the source, and also the elemental volume that's being irradiated. And then you can take the projector or the receiver and move them through the water to sample different angles. And if you sample from 0 degrees to 180 degrees or pi radians, then you've sampled the full VSF, at least in one plane. And then we make a very important assumption that there's azimuthal symmetry, and Zhongping talked about this as well. In almost all the work that we do, I'll talk about that more in a minute, but it's an important assumption, underlying assumption that isn't often recognized in these measurements that we make. So as both Zhongping and Darius mentioned, the VSF is very, very forward peaked. So this is a polar plot. I like looking at VSF sometimes in this format. So each ring here is an order of magnitude. And then the incident ray is coming from the bottom and it's scattered in the center. And then this is the distribution of intensity. But you can see many orders of magnitude peaked in the forward direction relative to the backward direction. Log scale, it's like 10.7 dynamic range. So a very, very large dynamic range, which means that if you were going to use a single detector and try to sample all those different angles, it has to be a very special detector that has, it's like gain switching to be able to sample across that large dynamic range. On the right are some VSFs that that were measured actually at Scripps Pier in 2008. And you can see some of the different shapes. Sediment laden has higher relative backscattering. So this is VSFs that have been normalized to the integrated volume scattering function, which is really a B from 10 to 170 degrees, which is what we're resolving with the sensor that we're using. But there was significant variability in shape of the VSF, and that's related to the types of particles that are there. There was a plot shown earlier about bubble-laden hydrosols, and you get this mid-angle peak, which is very, very interesting and very unique. And it's purely because you've got this perfect sphere going through the water. And it's very easy to simulate that or model that with mean theory, Lorentz mean theory. Yeah, so typically, if you look at the backward hemisphere, which is in this polar plot here, just this bit here, if you were to integrate this area, that fraction of the VSF is only about 0.3 to 3%. In very rare cases, it can be higher, but and we're talking about just the particles, because once you add water, especially in clear water, the water tends to dominate, and the water has a backscattering ratio of 50% because it's symmetrical around 90 degrees, as Zhongping mentioned. So Zhongping slid a slide on this. I'll show another slide on it, different way of looking at it. But yeah, so when you integrate the volume scattering function, you get total scattering B. And one way to look at that is in the unit sphere. So the key thing to understand is where this 2 pi sine theta comes from. And the sine theta essentially weights the volume scattering function in terms of its B contribution. And so and Zhongping had a nice plot on this too, but you have this annular ring essentially at any angle. And this is that implicit azimuthal symmetry that I was mentioning before. So we're measuring, what you do is you measure scattering at one angle relative to the source coming from the bottom. And then you assume around all the other azimuth angles that you're going to get the same value. So the perimeter of that is going to be 2 pi the radius, and the radius is sine theta. So that's where the 2 pi sine theta comes in. And that gives you the units of steradian. So the 2 pi sine theta effectively weights the distribution. And what's really interesting is even though you have scattering at 0 and 180 degrees, because of that sine theta weighting at exactly those angles, it doesn't contribute to B at all. So the scattering components, as Zhongping also mentioned, you can partition them. So this is partitioning total scattering in terms of the water component, BW, and the particulate component, BP. It's possible certainly to further partition BP, but in practice, operationally, it's very difficult to try to partition phytoplankton. You can partition things like, well, you can partition, like, for instance, different filtered classes, like size classes of particles, and people have done that. But you can try, yeah, so what people have done also is taken a sample, collected on a filter, and then combusted, so you get rid of the organic material, and then you measure the inorganic material. That's how Stavin measured his B of the PIM and the POM. But operationally, it's very challenging to make those kind of measurements. In respect to the angular distribution, of course, you have this integral that I just talked about, and you can change the limits of the integral. So 0 to 180 or pi radians is going to give you the total scattering B, but you can also look at the forward scattering, which is 0 to 90 degrees or 0 pi over 2 radians. You can also look at back scattering, which is pi over 2 radians to 180 degrees. So the primary scattering components, and just it's exactly what Zhongping has, so we're like completely copacetic on this, but pure water, turbulence. Turbulence is really refractive index discontinuities in the water. So you have obviously temperature and salinity, and that primarily is what determines refractive index of the water. And you have micro gradients in TS. So, and then sometimes you have very large gradients when you have like a river outflow, et cetera. But even in cases in the open ocean, you still have micro gradients in refractive index. So this creates, as light passes through, it's going to deflect the beam a little bit. So that's turbulence, and it's typically at the very, very small angles where you see that. Particles are obviously very, very important, and they really dominate in most locations the color that you're seeing in the water, and bubbles. So other scattering properties, if you normalize the volume scattering function by the integral of the volume scattering function, total scattering, it's known as the phase function, and it has units of just steradians. It's a function of angle. And then the backscattering ratio, BB over B. And then there's something called the asymmetry parameter, mean cosine, and it's a way to take the VSF shape, which can have a lot of different shapes, and kind of consolidate it into one shape parameter. It's kind of crude, but it can be useful in some situations. So if it's symmetric around 90 degrees, this G parameter is 0. If it's highly skewed in the forward direction, it approaches an asymptote of 1. In the ocean, almost in every single case, we're highly skewed towards 1. So these G parameters are usually always greater than 0.9, typically like 0.94 to 0.96, somewhere in that range. So here on the left is a plot of some VSF measurements from Santa Barbara Channel. I'll go through the different measurement considerations and then talk about the plot a little bit more. But because you've got 6+ orders of magnitude and intensity from near forward to backward in a single VSF, it's a real challenge in trying to measure that, especially with a single detector. There's also several orders of magnitude dynamic range at any single angle. So if you go from coastal water to open ocean, you've got this VSF, going over another several orders of magnitude. So you've got a huge dynamic range you need to try to resolve. There's rapid variability in particle fields, especially in surface waters. You have breaking waves. You've got bubble injection, foam at the surface. There's a lot of things going on, and certainly in things like coastal waters where you have surf zone as well. There's a lot going on. We've done some work there, but it's also a challenge. Rejecting ambient light, especially in the backward angle, because most of the light is scattered in the forward angle. So in the backward directions, you don't have much light back there. So rejecting the ambient light can be challenging, especially at the surface where you have a lot of ambient light. Calibration is a challenge too, because there isn't absolute standard. Like you can't go on Amazon and say, I want exactly water that has this exact VSF and put it in there, then it would be perfect. So there's a couple different ways currently. It's kind of the state of the art of calibration, which I'll talk about in a minute. Yeah, and errors can grow at higher turbidities and path lengths. So you start to get scattering along the paths, like in this diagram on the right here. You start to get scattering along these paths. So you could scatter before you get to the sample volume and scattering after the sample volume. We have correction algorithms for those, but if turbidity gets too high and that scattering is too much, then it becomes a problem. There's limits to what the algorithm can correct for. And you have to know something about the particles that are scattering, which is exactly what we're trying to measure. So this is an instrument that we first built in 2005 called the MASCOT, which stands for Multi-Angle Scattering and Optical Transmission, although the optical transmission part is not on the sensor anymore. But we have a laser in this housing on the right here, and it goes through a wedge depolarizer. So we have unpolarized light coming out, which is very important for just the typical VSF measurement. It goes through this Gershon tube, and there's also reflecting mirrors inside to clean up the beam. So we have a very clean beam, collimated beam coming out. And then we have an array of detectors here. And the array of detectors is convenient. It measures between 10 and 170 in 10-degree increments, but it's convenient because, as I was saying, you have this enormous dynamic range that you need to resolve. If you're trying to do that with one detector, it's a real challenge. If you have a bunch of detectors that are tuned for specific dynamic ranges, it's a lot easier. And then you can also do things like the field of view of the detectors you can change, because in the forward direction, it's very, very forward steeply peaked in the forward direction. So we need small field of views for that to resolve it accurately, but we can open up the field of views in the backward direction where it's more flat. And when we do that, we're collecting more light as well. So there's advantages in doing that. This is another sensor that's developed at Sequoia, where Wayne used to work. This is a slide, I think, that Matt Slivkoff at one time put together, and he's arriving later today. You guys will meet him tomorrow. But this measures near forward scattering through diffractometry. And you've got this laser, so another laser collimated source going through the sample here. And then there's a converging lens that focuses the light all from a single angle. So this light, whether it's scattered from the beam here or here, anywhere in this sample volume, it ultimately is going to make it to a single location on this silicon diode detector. And this has 32 partial arc detectors, so it's measuring 32 different angles in the near forward direction. So yeah, it's a really cool instrument. So what I was saying before, actually, right here, this plot on the left that I was going to talk about in a minute, this is actually the only real way to put together a plot like this with such a large dynamic range, is to use two different techniques. So we use diffractometry with the LIST VSF or the LIST 100 to measure the near forward scattering. So that gets us out to about 10 degrees here. If you can see, there's like a little bit of overlap out here. And then from 10 degrees to 170, we're measuring with the MASCOT. What's really, really good, like in optics in general, any kind of sensor development or sensor testing, if you have different techniques to measure a similar parameter, and then you compare these two different techniques and they match, it gives you a lot of confidence that you're doing something right. And so these two sensors use totally different measurement techniques for the VSF, and they're calibrated in very different ways as well. And the matchup here, around 10 degrees where they overlap is very good. So yeah, the LIST VSF, this is a version of the LIST. It still has all the diffractometry stuff, but they've added this thing called a roving eyeball. And there's a video you can watch on YouTube. Down here is the link. But this roving eyeball essentially looks at different parts of the beam that traverses the sample volume here. So when it looks at different angles, you're getting different parts of the VSF. And it's got this rotating prism here, which allows you to look at these different angles. So it rotates around. And what's nice too is that then it goes through a polarization splitter as well. So it's giving you polarization elements. So this is a very nice device. So you get the near forward scattering. It's, I guess, not polarized. And then the mid angle scattering, you get out to about 156, 158, something like that. And you can resolve the polarization with that. This is an instrument that Wayne developed. I don't know if Wayne, you're going to talk about this later, but this is a hyper BB rather. So it measures hyperspectral beta from 430 to 700 nanometers, and it's developed. I don't know if Matt's if you're going to talk about it, Wayne, but yeah, it's another sensor to measure BB. This is another VSF sensor. This was developed at HCG. This is an interesting design in that your sample is in here, and the beam passes through the sample this way, and then around the sample is this reflective conical mirror. So it reflects the VSF essentially from the sample down through this telescope down onto a CCD camera. So this is what the raw image looks like. And then with good calibration, you can get a VSF. But when you see stuff like this big tail up on the back end, what happens when you have samples that are enclosed in a volume, it's very, very difficult when you pass light through it not to get residual reflections in that tube, in that container. And there's actually some of these sensors that I'll show you go through extreme, measures to try to avoid those reflections. But this is a good example here on the end here that there's probably some reflection within that tube. This was also, I think, measured by Zhongping. The MVSM was developed in the Ukraine, and David Gray, or Derek Gray at NRL in DC has collected a lot of data with this, and there's a lot of Zhang and Gray et al. Pubs that use this data. It's a very interesting design because the light comes into the sample here, and your sample's right in here, and then there's a periscope prism, the specially custom designed prism that takes the light and scatters it down onto this photomultiplier tube. So this prism can rotate around the sample, and as it rotates around the sample, you essentially map out the VSF. And then it can also give you optical transmission, attenuation straight through the sample as well. This is the pole VSM that was developed at Villefranche. This is Malik Shami was the PI, but I know David Antoine was intimately involved with this sensor as well. But this is kind of what I was talking about, like extreme measures to avoid any reflections within the sample, where your source beam runs through the container holding the sample to another prism over here that takes it out entirely out of the sample. And then there's the detector that rotates around the sample to measure the VSF, and it's supposed to minimize the reflections within the container. This is a benchtop VSF that I have in my lab from Brookhaven. They call it a goniometer, which is another name for a VSF measuring device. And it's just, there's a sensitive PMT here on this rail that rotates around. But you can see here in the backward direction, so this is like, I think it was Darius showed that you get these oscillations with when you have spheres in solution of different sizes, and it's this constructive, deconstructive interference of the beams. But this right here, this deviation at the large angles is due to the internal reflections in that cuvette, like I was just talking about. And then a very, very popular sensor, especially for ocean color studies, validation, et cetera, is the Wet Labs Eco. This was first developed and commercialized in 2000. This is something that I helped develop, and also the calibration, protocols and stuff like that. There's multiple iterations over the years, different ways it was packaged with different angles and different colors, et cetera. It's been deployed on a lot of different platforms. There's versions with copper shutters, like up here in the upper left, so you can keep it out on a mooring for many, many months and still get accurate data. So this guy, Matt Slivkov, coming tonight, he's president of, or co-president of In Situ Marine Optics, and they've developed their version of the ECO that has 6 different wavelengths and has a much, much larger dynamic range and some better optics, to be honest, too. But it's a very good choice, especially if you're operating in very turbid waters to very, very clear waters, because it can really resolve that full range. So to get into the VSF measurement and the calibration, what's really important to remember is that the beta is always resolved over a range of angles. So even with the mascot, with these discrete detectors I had in that arch, in that array, there's a range of angles for each one of those angles, and we published that in a paper, so you can get the weighting functions essentially as a function of angle. With the eco sensors, you have a very broad source beam and a very broad detector beam that intersect, as shown in this subplot A. And that was intentional to make those beams as big as possible. We're trying to get as much light as possible into the detector, but we're also using it not to really measure the VSF, but we're really trying to derive the backscattering coefficient. So we're trying to resolve as much of the backscattering part of the VSF as possible. But because of that, there's a weighting function that, and it's a weighting function is a function of angle that defines that particular geometry for that particular measurement for that particular sensor. And we have a paper that goes into the detailed calibration methodology, which I don't have time to talk about. But once you get this weighting function, then you can take the volume scattering function, convolve it with the weighting function, and it gives you this weighted beta. So even though the eco has these very broad source and detector beams, they still say, you know, it's measuring at 124 degrees. But you have to remember that's just a centroid angle and a very, very broad weighting function. Yeah, so this goes into a little bit how we determine the weighting function. There's really two ways to do it. You can do it experimentally with a plaque. So this is a Lambertian plaque that you move through the intersection of those two, the source and detector beams. The problem with the plaque, or a problem with the plaque, is that if you have a diffuse plaque inside of a container, you know, with water, is that light kind of goes everywhere. So these weighting functions tend to be a little broader than they are in real life. The other way that, and the way that we're doing it now, we've done it for many, many years, is do it analytically. So have a virtual plaque that you move through and then go through all the analytical calculations to resolve how much power you're getting. So at each location, each one of those dVs in that plaque, you can calculate how much power is being scattered back to the detector. And then you can attribute it to an angle. And then we go through and step it through, and then you just keep on, you know, piling in the contribution for different angles, and then you get a weighting function, which is what these look like. So initially, it's gone through some revisions over the years. These red triangles that you can see here for the three different angles of the eco, the standard eco BB or the eco VSF. Those we realized at some point were much too narrow. So there has been some revisions over the years. The current version of the weighting function that we're using is this dashed black line. You can see just how incredibly broad it is. It's peaked at 124, but it goes almost to 180, and you're even getting some forward scattering in here, like shorter than 90 degrees, smaller than 90 degrees. So what you do is, if you have the weighting function, just to briefly talk, I don't think I have a slide on the I don't really have a slide on the calibration. I used to have a bunch of slides, but I'm just trying to trim it down. But you put in then, like I said, there isn't like a sample you can buy from Amazon that has like perfect VSF. So you have to suspend microspherical beads in solution, very, very clean solution. And then with the beads, with Lorentz-Meath theory, we talked about how we can calculate what the scattering properties of spheres are. So we can calculate what the phase function is. The phase function is, remember, is the volume scattering function normalized to B, the total scattering. And we don't want to have to worry about understanding like exactly how many beads we have in that vial, in that sample volume. So we use a AC9 to resolve B, and there's no absorption here, so we can use the C measurement from an AC9, which I'll talk about in a minute. And that gives us a measured beta over B. It's really raw counts over B for this sensor. And since we have the beta over B from the theory, from Lorentz-Meath theory, we can use that to then change counts into the volume scattering function, if that makes sense. So if you like more detail, this Sullivan et al. Paper that I've referenced there, ooh, that's a touchscreen. Yeah, this Sullivan et al. 2013 goes into gory detail on all of that stuff. And of course, you could contact me as well. Yeah, so as I mentioned, the real objective of these sensors and what people use them in the community for typically is to get the backscattering coefficient, but you're only measuring this beta at a single, I won't even call it an angle, it's a range of angles in the backward direction. The ideal sensor for measuring backscattering would be to have that that sine theta weighting function that I mentioned, you'd want to be measuring that exact sine theta weighting function. We tried to develop a sensor at one point to do that. It worked pretty well, but it was never commercialized. But in this case, it doesn't look like that. So you need a conversion. So we have this chi factor here that's used as a conversion for the specific beta, and I should rewrite this as the beta p, and it's the average. So it's really theta with a bar over it. So that's a specific measurement we're measuring with the eco, and then this chi factor has been looked at in a number of studies. This study from Sullivan and Twardowski came up with 118 is the best angle, but there's a specific chi in the Sullivan et al. 2013 paper for the eco, and that's the chi that converts this beta to the backscattering coefficient that we use in all of our measurements and all of our algorithms, et cetera. So just the key points here, remember the beta measurements are always made over an angular range. And if you see a publication where this is beta 120, just always remember it's 120. Is it a wide angular weighting function or a small one? It makes a big difference, especially if you start to include some of that forward scattering, because as we saw, it's very, very forward peaked. There's an implicit assumption necessary about VSF shapes in the backward direction. So this chi factor is assuming there has to be some shape. And through other work that we've done, we've shown that, and I'll show this in a minute, I think, that the shape in the backward direction is relatively consistent. So we think that this chi factor is a pretty, the associated any bias errors from this assumption of the VSF shape being constant in the backward direction are relatively small. Wanted to add a slide here in turbidity. You know, we always talk about turbidity, and you can go out and buy sensors that measure turbidity, and they have these nephelometric turbidity units. These sensors typically measure scattering at 90 degrees, but many sensors use angles other than 90 degrees. The Wet Labs turbidity sensor, you can get it on an eco format, actually uses, I think, 140 degrees. So there's a lot of variability there. The spectral characteristics vary. Some use white light, some use 880. The Wet Labs one, I think, uses 740. The angular weighting varies, and then it's calibrated to formosome particles, which their scattering properties aren't really anything like the real ocean. So all the different turbidity measurements as a result are really different. And even though they have what sound like very specific engineering units, NTUs with different sensors are going to give you totally different values. So it's typically not a rigorous optical property. It's not really water clarity. The best kind of optical parameter, optical proxy for water clarity is C, the attenuation coefficient. And oftentimes it may not be correlated even with backscattering. So how do we measure total scattering? So there isn't currently on the market any sensor for measuring total scattering. We actually developed one, myself and Ed Fry, several years ago. It actually worked pretty well, but it was never commercialized. And it used a totally different method. But the standard practice is to use an AC device. An AC device from Wet Labs, there's an AC9, which has 9 wavelengths. There's the ACS, which is hyperspectral. But it has one tube, and we're going to have a practical on this, so you guys are going to be intimately familiar with the AC devices. But one tube measures absorption, the other tube measures attenuation. And the hyperspectral version has this filter wheel that incident light beam traverses that separates or disperses the incident light into all these individual bands, and that's how it measures the spectral, hyperspectral absorption and attenuation. The AC9 has discrete interference filters on that wheel, nine discrete interference filters. And there's been, when it first came out, there was a lot of work just demonstrating that the AC9 and the ACS were measuring very, very similar things, and that's what this plot from Sullivan and Donahue shows. Here are the 9 individual points from the AC9, and it falls directly on the hyperspectral ACS. And those spectra also match in culture lab measurements from a spectrophotometer really well. So A plus B equals C, so you can derive B with those measurements. So just to quickly go over the measurement of beam attenuation from a transmissometer, you have a collimated light source. So this is just like our laser that we put through the fish tank yesterday. And we have a detector, and then you have a beam splitter on the front end, so you can measure how much light is going in. If you know how much light is going in and how much made it through your fish tank, then you can estimate the transmission, and from the transmission you can get an attenuation coefficient. This design, as I have it here, though, is a problem because there's a lot of scattered light that reaches the detector. So remember, with an attenuation sensor, we're trying to measure light out here that's passed through the sample without being scattered and without being absorbed. So we don't want that forward scattered light. So the way we do that is to move it back, and then you have collimating optics on the back end as well. So that way, you're only looking at the light that passed through without being scattered or absorbed. However, yeah, in the ideal attenuation meter has an acceptance angle of 0, but if it's exactly 0, then you're not measuring any light. So there's a compromise that all transmissometers, all beam attenuation meters, like the AC device, like there's the LIST Tau now at Sequoia, the LIST 100, all of these different attenuation meters have to make some compromise in terms of an acceptance angle. With the AC9, the acceptance angle is 0.93 degrees. There's actually a lot of scattering between 0 and 0.93 degrees that's being collected by this that we don't want. So what it's really measuring is the absorption plus the integral of beta from 0.93 to 180 approximately. And each transmissometer again has a different acceptance angle. So you can't take C measurement from a list and compare it directly to C measurement from an AC9. They're going to be very, very different. And because of that, it's very important in any publication with a beam attenuation measurement that you record in your methods what that attenuation acceptance angle was. Yeah, this is important. I actually had a slide on this before, but I took it out. But the optimal accuracy is reached when the path length is approximately 1/c. So if you're trying to measure C in water with a attenuation coefficient of about 1 inverse meter, a 1 meter path length is optimal. And you've got an interplay there of the longer your path, the less light that your detector is seeing. So at some point, you're going to be running against the detection limits of that sensor. But if it's too close, the path length's too short, you're not going to have enough attenuation through the water to get good resolution capability between that light that passed through versus the light incident into the tube. And so there's a bunch of theory that goes, which I think is super, super cool, but the optimal accuracy is this 1/c. So in very clear water, the path length for the AC devices is 25 centimeters. So that's really optimized for water that's 4 inverse meters C. That's very, very turbid. So that, like the horizontal visibility is less than a meter in that water. So the reason ACS still does and the AC9 still do really, really well in clear water is because they have very good optics and very good dissolving capability, signal to noise essentially. But in the past, especially like the 70s and 80s, there was a lot of effort made to build really big benchtop attenuation meters and absorption spectrophotometers for trying to resolve very, very accurately optical parameters from open ocean water. But they're very, very impractical, and obviously it's not a sensor you could put into the ocean. But now with modern electronics, we can get good signal to noise even in very, very clear water with these sensors. So on the absorption tube, it's a reflective tube. This is something that Ron Zonnefeld designed when it first came out in 1992, over 30 years ago. But you've got on the source end, you've got the same. You've got a collimated beam that goes through a beam splitter and then the tube. And then on the end of the tube, you have a detector behind a diffuser. And the detector is right up against the end of the tube because with absorption, we're trying to collect all the scattered light. So we want to collect all of that. You're only trying to measure the light that's missing from absorption. So you want all the scattered light collected. So with this model, and this model it's a glass tube around the sample, and then there's an air pocket behind the glass tube. And that gives you a total internal reflection of 41.7 degrees, which you guys measured yesterday in the tank, if you recall, with the laser pointer. So you validated that. How many got 41 or 42 degrees? I know there was a few teams that got like 40, something like that. Yeah. Yeah, and so this is what like an integrated sensor package looks like. So Mascot is sitting there on top, and then there's 2 AC devices back here. There's a list measuring the near forward scattering on top, and then there's some eco sensors on the bottom, and they're all multiplexed together with a data handler, et cetera. Yeah, and so this is what the data looks like when you add up the list and the mascot. And it's a good indication. We were very, very curious to see what these would look like when we first made these measurements. And in general, you can actually see quite a bit of variability. You know, we're talking about, this is like 8 orders, 7, 8 orders of magnitude. And you can see sometimes you get these really interesting shapes. So we published some work on this and did a lot of modeling to describe that. Another way that you can test closure is, so we've got the mascot in the list, and they match up really well in that kind of 10 to 12 degree area of overlap. But we're also measuring B from the AC9. And we know B from the AC9 has an acceptance angle of 0.93 degrees. So we can take our mascot plus list VSFs, we can do the integration to get a B that should be copacetic with what we're measuring from the AC9. So we use that 0.93 acceptance angle to 180 degrees. For the most part, they agree pretty well. You know, at higher Bs, there's some divergence there. But the key thing to understand with B from the AC9 is when you have a derived property, so you have C measurement, you have the associated errors, potential bias errors, et cetera, with the C measurement, and you have the A measurement. And the A measurement is actually more complicated. There's a very large error because you have this total internal reflection of 41.7 degrees, but you're not getting all the scattering from 41.7 to 180, and you need a correction for that. That correction can be 20, 30% of your total signal that you're measuring. And it's oftentimes, there's a bit of guessing. There's assumptions, let's put it that way, that goes into that, which I'll talk about in a minute. Actually, you guys will be intimately experienced with that after the practicals, which you're going to have to apply the scattering corrections to A. So anyway, there are potentially large bias errors with both, particularly A, somewhat with C, and these will also propagate into B. And whenever you have a derived property, any errors from all the parameters you're using to derive that final property that you're interested in, they all propagate. And you know, if they're bias errors that we can quantify things like random systematic errors, and I can put error bars on this. But the bias errors with the assumptions that are made are much more difficult to try to quantify. So in general, this isn't too bad. And then what's interesting too, you can look at the cumulative scattering distribution. We know that there's a lot of scattering in the forward direction relative to the backward direction. What this does is here we're integrating to get B, but B just over different angular ranges. So you can just integrate from 0 to 1, 0 to 10, 0 to 50, et cetera, out to 180. And if you do this, and so by the time you're at 180, you've got the full total scattering. And so your cumulative phase function here is 1. But this shows you that at 50%, you're typically around 3 to 4 degrees. So about 50% of the total scattering of total B is in that first few angles. It's really important to understand just how much scattering magnitude you have in those forward angles. If you guys have any questions at any time, please don't hesitate to ask. Okay. Yeah. So right. So you're basically folding it around. So you're increasing the path length, and the prism. I've seen designs where you can actually move the prism back and forth. So you could essentially, you can optimize the path length to the water that you're trying to measure, which is great concept. The trick then is attenuation meters are extremely sensitive to alignment, and the first AC devices that came out, they have these two, like the picture I showed, and you guys will see it tomorrow, but you have two housings, a source and a detector housing, essentially. There's a lot of other stuff in there. And then you have the two tubes. And the first design that had come out, it had 3 rods that was kind of holding it all together. But you would calibrate it, and then you would hose clamp it into a cage to actually take a vertical profile, and you get really crazy values. You wouldn't get consistent values. And then you put it back on the bench top, and it would be working again, like exactly how you expected. And so we figured out that was because when you were hose clamping it into the cage, you were actually changing the alignment just a little bit. Because that beam, when it goes through collimating optics on both sides, you're focusing it down to a pinpoint in a field stop, and invent a detector behind it. And it's very, very sensitive to that alignment. So when you move a prism back and forth, if you do it in a way where you can maintain perfect alignment, it can work. Or, I mean, another possibility is like you get it kind of configured the optimal way for the water that you're interested in making the measurement in. And then you calibrate it. You just don't move it at that point. You calibrate it, you make your measurements, et cetera, and you just go through that process every time you want to change the prism length. But yeah, do you know of a sensor? I mean, I've always been fascinated by that design and would have loved to. Oh, okay, cool. Yeah, yeah. Okay, yeah, cool. And it works well. Yeah, okay, I love it. Is it custom or does somebody sell that? Okay. Yeah, cool. All right, great. Good question. Any other questions? I'm sure there's. All right. Yeah. And the what? Yeah, it's a good question. So the list 200 is an upgrade to the list 100. It makes the same measurements, though. Correct me if I'm wrong, Wayne. It's the B and C. Yeah. So that's specifically for absorption, and this is a scattering talk. I do have a lot of slides on that, and I've actually been working with. Yeah, we've been working with Wayne for years now, developing a new hyperspectral absorption meter that uses the SciCam, the point source integrating cavity type design. We have benchtop SciCams in my lab, and we also have actually the Sunstone company sells them as well. They're the same version that Rudiger Rockers uses in his lab in Germany. But yeah, it's we're getting like tremendous like signal to noise with this, and I sound like Trump, tremendous signal, and it goes into the UV as well. It goes all the way to 300, where it gets a little signal to noise. It has some signal to noise issues down there, but like 320, 340, it's still good. So for pace algorithms and stuff like that are starting to go into the UV because pace resolves into the UV down to about 350 now. It's really exciting. That's the Hyper A. Yeah, yeah, exactly. Yeah. And for radiative transfer theory, when you're trying to understand, like maybe basically map out the full light field as it propagates through water, the two like critical pieces of information are the absorption coefficient and the volume scattering function. If you have that, you have pretty much everything you need. There's some little details like you could have fluorescence and inelastic, Raman, things like that going on, but those are the two things you need, which is why we put a lot of effort into the VSF measurement over the years. But absolutely, yeah, with the VSF measurement resolved with something like a list and a mascot with the Hyper A, you've got like everything you really need. And then you have a way to validate that with something like an AC9 attenuation sensor. Yeah. Yep. It was a good way to tie it back into scattering there, the absorption. So Zhongping also talked like we had a mind meld and we didn't even know it because we have a lot of the same slides, but same concepts at least. But analytical modeling of the VSF is very important. If you can do it in an analytical model, then it's easy to write algorithms. And if you have algorithms that describe the VSF, then you can make measurements and potentially invert that to understand properties of the particles, which is really the ultimate goal for all of us in doing remote sensing or making these optical measurements. So I'm not going to spend a lot of time on this. Basically, the Henier-Greenstein was something that was developed for really astronomy. and it was trying to adapt to the ocean, and it always did poorly. And so, like George Cadwar and Vlad Holtrin came up with a two-term. They kept on trying to refine it to try to make it work with the measurements that were made. It never really worked, so I just wouldn't recommend it. Kopelovich, which also Zhangping mentioned. Kopelovich, they basically, this is very, very interesting because they, out of like all the different shapes that they measured, they found that you could have two basis vectors and mix them in different ways, and you could pretty much reproduce most of the shapes that you measure in the ocean. And we've tried this. We have a very extensive data set now of VSFs. We've tried this with our VSFs, and it actually works really well beyond about 0.6 degrees. So in the very small angles, has some issues, but it's surprisingly good. And there's really just one parameter that you need. It's a one parameter algorithm, which is really unique because that's just the mixing algorithm, essentially. Sorry? Okay. Yeah, okay. And then, as Zhangping also mentioned, Fournier-Ferrand is currently the state of the art. And this is really an outstanding model. George Fournier really knows what he's doing. And for the VSFs, where we have the full range that we can resolve between 0.079 degrees and 180 degrees, it fits super, super well. Very low residual errors. It's just terrific. The inputs are also the power law slope of the size distribution. So it assumes the particle size distribution is a power law, which is a great first order assumption. Some people will argue with that, but it really is a very good first order assumption. So that whole model is, you can describe the shape by just one parameter, the slope, this mu, and then the bulk refractive index of the particles, n. So those are the two inputs. So if you can go out and make a good VSF measurement, you then have everything you need to invert it to try to solve for the slope, the power law slope of the size distribution and the refractive index of the particles. So it's a very potent, very, very nice algorithm. So in the backward direction, I mentioned that we haven't found a lot of variability in the shape, and that was really emphasized in the Sullivan and Twardowski paper from 2009. So we took the mascot out all over the world, all different types of water, over 7,000 1-meter average measurements. And in each 1 meter average measurement, there's lots and lots of measurements because it's measuring at 20 hertz, 20 times a second. So what we're doing here is we're normalizing all of those VSFs to the integrated backscattering coefficient that we're measuring with the mascot. So what we're showing here is you've got the circles, which are the averages, and then the standard deviation of all the measurements that were made. And there's shockingly little variability. Based on basically a lot of the theory up to that point, we expected to see a lot of changes in shape in the backward direction, and we just didn't see it, which for a lot of applications is tremendously useful. If you can make the assumption that the shape of the VSF isn't really changing in the backward direction, for things like, for instance, remote sensing, because remote sensing, you've got the sun moving across the sky, and at any point, you've got your detector and the satellites. You got all these different backscattering angles that you're measuring ocean color. And there's a whole algorithm called the bidirectional reflectance distribution function, basically normalize all those disparate measurements to a common geometry of looking straight down with the sun straight overhead, which is, you know, purely fictional. But that's where all the ocean color data, all the maps that you guys get, those all have that BRDF normalization. It's a very, very important thing. But if you can make you have to make an assumption of the volume scattering function, because the volume scattering function completely drives that BRDF, because at all these different source, you know, the sun and satellite detector angles that you're making in water, that's the VSF. So anyway, if you can assume that it's a relatively constant shape, it dramatically simplifies those algorithms. Yeah, yeah. Yeah, there is some inconsistency in the literature, though, like with the MVSM, Derek Gray and Xiaodong Zhang have published data that shows a lot of variability in the VSF. We've actually made measurements of the mascot in a lot of these same areas, including Sabre. We were on the same cruise. And honestly, this seems very unrealistic to me. That just, you know, Zhang Ping isn't here to talk about it, or sorry, Xiaodong isn't here to talk about it, but it seems unrealistic. Yeah, I have some hypotheses as to why, but I won't go into. And this is more evidence that a constant shape in the backward direction appears realistic, because if you go through radiative transfer simulations, assuming a constant VSF shape in the backward water in backward direction in diverse waters, and you have measured remote sensing reflectances and simulated remote sensing reflectances, and these all have different solar zeniths, so all different kinds of BRDFs, you get a very, very nice relationship. And then when you look at the bidirectional reflectance distribution function, assuming a constant shape, it also does a very, very good, very good job. It matches full simulations with hydrolite really, really well. So there's just, I'm trying to say here is there's just good evidence that that shape, being constant shape in the backward direction, is likely quite valid in the vast majority of the ocean. Even like places like Lake Erie, massive blooms, we still see that same shape, and that's included in the data that I showed before. Okay. So to go back to the primary scattering components in water, now we're going to go through each of these individually. So Zhangping mentioned scattering by pure water, the state of the art is Xiaodong Zheng's work. This is all theoretical, but it's been validated and it matches experimental work, like the best experimental work ever for measuring scattering by pure water. This was done by Morel in 1968. So it's a French publication, but he went through extreme measures to make these measurements, and it agrees within 1 to 2%. The big update with his application of this Einstein-Smoluchowski theory that it's based on is he used is an important depolarization ratio. It's really all you need to know. It's the primary reason it's different from other publications like Morel 1974, which is widely cited. Morel used a depolarization ratio of 0.09, and Zhang, through this work by Farinado and Rolwell, 1974, they made their own measurement showing it was 0.039, and it makes a big difference. It's about a 10% difference. So yeah, so we think there's maybe about a 2%, plus or minus 2% possible error with scattering by pure seawater using this algorithm, which is very good. And then as Zhangping mentioned, the seawater angular distribution is symmetric around 90 degrees. So if you want backscattering, you divide by 2. So for a part of the, or for the practicals with the AC device, you guys are going to get Xiaodong's code to calculate pure water scattering. So you're going to get that soon. Yeah, and so scattering in clearest water. So this is the South Pacific Gyre. So this is some of the very, very clearest waters of the world. Zhangping showed cases where, so yeah, so this right here, these colored lines. So you got the black, the green, and the blue. These are 3 different models for pure water scattering at 117 degrees. So this is a specific angle. In this very, very clear water, so what you measure when you take these scattering devices, really all the scattering devices, when you take them out to the ocean and make the measurement, you're measuring total scattering. So if it's total, yeah, whatever the total VSF, whatever measurements you're making, it's a total. So it means it's got the water and the particles together, which is different from an AC device because you calibrate it with pure water. So just like a spectrophotometer, when you make the measurements in the ocean, you're measuring the absorption and attenuation of everything but the water. VSF measurements are different, that you're measuring the total of everything. So if you want to get what you're typically interested in is the backscattering or the scattering due to the particles. If you want to get the particles, you have to take these totals with these particular error bars and subtract out the pure water to get the particulate betas. So the point here is that accuracy is very, very important in very, very clear waters because the water component is so much. So here the water component is almost 90%. So the backscattering ratio is very, very close to probably 40%, something like that, because the water is completely dominating. When it's just pure water, it's 50%. So turbulence, I just showed one plot on turbulence. So there's been some work looking at scattering by turbulence. And again, these are refractive index discontinuities. So you can look at different temperature differences This one is 0.9 degrees, but you can have small temperature differences and large temperature differences. And so Derek Bogutsky developed a device to look at this, but you do get scattering. But the scattering, you can see this is out to 0.057 degrees, so it's very focused in the very forward direction. Turbulence is not included in most attenuation measurements. It's just very, very important because the acceptance angle is small enough, but the exception is the list. The list has a very small acceptance angle. So, and this was intentionally done with the AC devices, so that's why it's 0.93 degrees. So even though, I mean, you can never get a perfect attenuation measurement to begin with, and there has to be some kind of compromise there, but it's typically used as a proxy for like the concentration of particles in the water, TSM, stuff like that. So it works fine for those kind of proxy biogeochemical estimates. But if you want to do actual radiative transfer and you want to use that C from an AC device, you have to make a correction for that 0.93. You have to figure out what's going on there. But just to show you with the list, this is a case where this is a deployment off Hawaii. Matt Slivkov actually put this together. Again, he's coming tonight. But on the left, we have the change in refractive index calculated from TNS as a function of depth. And then on the right is what we call the turbulence indicator from the list VSF, which is essentially the ratio of the most near forward angle with a larger angle. And they matched up really, really well. So that's just showing you, yeah, it does measure turbulence. That wasn't where it published. So to move, yeah, sure. You can put these sensors through flow-through systems on chips. And actually the MVSM that Derek Gray deploys with Xiaodong Zheng, that's primarily how he does it. He doesn't actually put it in the water. And there's actually a cuvette in there. So you're flowing water through a cuvette on the deck of a ship. That's where I think, honestly, some of the, I don't want to, he's not here to talk about it or discuss it, but there's bubbles that get in there and they're very difficult to get out, and it's very, very sensitive to bubbles, and you get multiple reflections in a cuvette like I was talking about before. So when you get those upticks in the back direction. So anyway, making VSF measurements, that's the biggest, really in a lot of optical measurements. You guys will understand this after you try to calibrate AC devices, but bubbles are your nemesis. They're a big, big problem. So to make VSF measurements through a flow-through system, you have to be very, very careful to get the bubbles out. The other thing too is that you have a lot of sensitive aggregates in the ocean. And if you start sucking them through a flow-through system, it just blows them up instantly. So and we've done some measurements on this. If you take measurements with an AC device, for instance, with a flow cell in there and you're pumping the water through like we typically do, if you compare that to measurements where you take the flow cell out, it's an open path, which is should be perfectly legitimate, way to make the measurement. They're different. And that's likely because we're blowing up aggregates, detrital aggregates, when we're flowing the water through. Okay. Yeah. There are very good like Venturi techniques to like remove bubbles and stuff like that. So, assuming that you guys have that, you're hopefully at least getting the bubbles out, but you may be disrupting the particle size distribution. But it'd be, an easy experiment to make the measurements to the flow cell, put in the water, and do that in different areas and see, how they agree. Yeah, Wayne, you seem pregnant with a comment. What's that? Okay. Hmm. And you get good agreement, or you get, okay, okay. Yeah, I know you and Emmanuel with Oasis did a bunch of this. Yeah. Um, yeah, I'm trying to think. I don't want to belabor the point, but there was one, you had a pump on with list and a pump off with list, and it was significant, very significant. Yeah. So to move on to particle scattering, any other questions? Okay. So as Darius mentioned, you have reflection off the outside of the particle. You have refraction. So this is light that enters the particle. There's a change in refractive index. Whenever you have scattering, it's because there's a change in the refractive index. All those little dipoles that Darius was talking about is another way to think about that is a refractive index distribution within any kind of particle. And if the refractive index of the material in the particle matches the surrounding water, then you won't get any scattering. And remember the carbohydrate beads that were blowing up, that's a good example of once it gets filled with enough water, you've matched the refractive index so well, you get almost perfect transmission. So, but there's really three different processes: reflection, refraction through the particle, and then diffraction. Diffraction is interesting because this is light that comes close to impinging on the particle, but it doesn't. It travels next to the particle, but the electrical fields from the particle influence the light, and it's scattered around the particle. That's diffraction. Diffraction, because you get that subtle scattering that gives you scattering in the forward direction, you typically see it really. So this hatched area here is all diffraction in the forward direction. So a lot of times diffraction is about half of total attenuation of particles, but it's just within the first like 10 degrees or less. Very important. Yeah, so as far as backscattering, there was a publication by Stramski et al. In 2004. This is a good quote. Our present-day interpretation and detailed understanding of major sources of backscattering and its variability in the ocean are uncertain and controversial. And we have done some model on what we call the enigma of phytoplankton backscattering. So Stramski had done a lot of work, and I think as part of what Zhangping was showing, where these different phytoplankton classes could be modeled as homogeneous spheres using Lorentz mean theory, which is the simplest theory you can use to calculate scattering. It's a really good first order thing to try. But when you do that, you get backscattering levels that are much lower to be consistent with their influence on remote sensing reflectance. So there's something wrong there. So it's an enigma. Either our models to predict what their contribution on remote sensing reflectance are wrong, or the homogeneous sphere is not a very good model. So one thing that we wanted to try was to test the complex particle hypothesis. So this is an experiment that we did maybe like 15 years ago, and it was never published. We keep talking about publishing this, but it's pretty cool. But anyway, these are different phytoplankton. We have Thalassiocyra, which is a diatom. It's got a hard frustral outer cover, cell wall. Catastrophe socialis is a colonial diatom that also has hard frustral on the outside. And then gyrodinium, which I think is called something else now, which has a hard chitin outer shell, it's a dinoflagellate. So we made measurements of backscattering ratios for each of these different types of cells. And this is what we measured for the backscattering ratio. So 1.3%, 0.6%, 0.4%, 0.4%. With me theory, we get much, much less values than what we measured. So this is basically consistent with what Stramski was saying, is they don't agree. And then when we use coded me theory, we actually get values that are in a very, very close agreement. So it looks like this shell is actually having a major, major impact on the backscattering, significantly enhancing the backscattering. So then we also rigged up this contraption with a microscope and a laser on the side where we can we had it at an angle where we could look at 140-degree scattering through the microscope, turning the light off on the microscope, obviously. So we're just looking at light from the laser. So we did this with a bunch of different organisms. This is one example. So this is the Thalassiocyra. It's like little pillboxes of the glass frustrals. And this is what it looks like with the laser backscattering image. So you get these very, very bright areas basically around the pillbox. You can actually take a Petri dish and do the same thing with a laser, and it shows the exact same type of image. So it was clear that that you need a high refractive index difference in order to get these very bright spots. And so we think this is really the source of the enhanced backscattering from these particles. We've done a lot of work looking at the backscattering ratio in chlorophyll. And on the left is the Gulf of California. On the right are lots of different locations around the coast of the United States. Very similar relationships. When you have high chlorophyll you see this kind of wedge going towards about 0.5%, 0.5% floor. So nominally when chlorophyll is very high, you've got the phytoplankton that are dominating. So if me theory was right, then you'd expect about an order of magnitude less backscattering ratio than what we're actually measuring in the field. But we never really see anything below 0.5% floor, even when phytoplankton are dominating. So it's very important. This is just another clue that phytoplankton likely do make a very significant direct contribution to the backscattering ratio. When phytoplankton gets lower there, you see a large range in backscattering ratios. So this is really in coastal waters where in some cases you have suspended sediments. Suspended sediment has high backscattering ratios, so you get a broad range here. It's really those case 2 waters that Zhangping was talking about. There's another study by Organelli et al. Where they looked at coated sphere model and tried to reproduce the measured C, the attenuation, and the measured BBP backscattering, particular backscattering. And the coated sphere model could simulate their measurements really, really well, where the homogeneous sphere model could not. Those are very good relationships. It was a very nice paper. So additional considerations with particle scattering. Any questions on that before I move on? Okay. These are just things that I think would be good for you guys to know. Backscattering ratio, we talk about spectral shapes. For size distributions described by a power law, which again is typically a very good first order assumption with relatively low absorption, theory predicts spectrally independent BBP over BP to the backscattering ratio. And that's even been shown in a case where Amanda Whitmire looked at cultures of phytoplankton. So in these cases, the power law assumption probably is getting a little shaky. But even in these cases, backscattering ratio was relatively constant in all these cases. There has been some measurements like David McKee made measurements in the Bristol Channel and saw some shape, but there's also big error bars here. So generally, it's a pretty good assumption. If you collect data, like when we go out and collect data sets, this is one of the proxies, like first things I like to look at to just kind of judge the quality of a data set. Because the BBP is measured spectrally, and it's calibrated completely independently from the B measurement. The B measurement comes from an AC9 or an ACS. And again, it's the C minus the A. So you're taking all these different measurements that have to come together for BBP over BP. But BB over B has a relatively small range, just one order of magnitude, like 0.03 to 0.3 to 3%. So with that one order of magnitude range, you're constraining, what's realistic, and you're looking for the spectral independence. So it's my favorite parameter to look at to see just how good our data set is when we're in the field. Another thing is anomalous dispersion. I don't know if Darius talked about this or not, but the key point here is that where you have absorption peaks, particularly with phytoplankton, the absorption affects the scattering. So even in cases where you get these big absorption peaks, the attenuation spectrum for this looks like a power law, almost perfectly. And this is because the peaks in absorption are compensated by dips in the total scattering. So when you add A plus B, you get this nice power law for C. So anomalous dispersion is that phenomenon that makes that happen. And then if you're looking at backscattering, you can get really interesting shapes, like around this chlorophyll peak. You actually see a dip in front of the chlorophyll peak, and there's a peak on the long wavelength side of the chlorophyll peak. And it turns out this peak is pretty much right at where chlorophyll fluorescence happens. So it could be confounding potentially chlorophyll fluorescence measurements and vice versa. So it's a very, very interesting phenomenon. And actually, we're starting to make hyperspectral BB measurements now. And for many, many years, we've been making assumptions like the backscattering spectrum follows a power law and stuff like that. And with these measurements that we're making now with With the hyper BB, we're seeing that's really not the case, or there's all these little bumps in there that actually are quite important. And pretty much, Stramsky looked at this in '88, Zonnefeldt and Kitchen looked at it in 1995, and I don't know anybody who's looked at it since. So if anybody's looking for a good thesis topic, I can recommend it. And then there's also scattering near 180, and this is a special form of scattering. So Darius was talking about coherent scattering when you have all these dipoles that are in close proximity, like in a particle, in a cell, in an organism. But when you have particles that are dispersed in solution, the assumption that we make so that we can add up all of these different particle subcomponents for these different particle groups is that there's incoherent scattering. That you have to make that assumption to be able to add them up. When you look at 180, you get some very unusual things happening, and you get something called the glory, which is actually coherent scattering between particles because you have light that's coming down and light that's scattered up at the same time, and so they're interacting. So it's a very interesting phenomenon. It's been measured a lot in the atmosphere. So there's this picture of the plane. Whenever you're in a plane and it's kind of cloudy around, you can usually see this glory phenomenon, this peak, essentially at beta 180, if you look down into the shadow of the plane. But it really hasn't been looked at much in the ocean. It's very important for things like LIDAR too. If you guys don't know what LIDAR is, it sends a laser into the water, and then there's a time-gated detector. So, and it's very, very fast. So you can actually remotely profile the backscattering through the water with a remote sensor. Very, very cool. There's been a big push by Hostetler and Mike Barenfeld for many, many years to put one of these in space. I think it'll happen at some point. It would be really, really great addition to the ocean color sensors that we have up there. But these LiDAR systems are essentially measuring beta 180. It's just time gated through the water column. So we really need sensing capability at beta 180, and currently we don't have it. It's a lot to do. Polarized scattering. So this isn't something that Zhangping talked about. So this is going to be a little new. So Maxwell, you did talk about that in 1964. First proposed that light was undulations in the same medium, derived a waveform for electrical and magnetic equations, and his work in producing a unified model of electromagnetism is considered one of the greatest advances in all of physics. So yeah, it's an electromagnetic wave, which you guys know. It's important to realize that polarization refers to the orientation of that wave, but specifically, it's the electrical field. So when we talk about, like yesterday with the laser pointer, we're shining it through water, and you could rotate it, and you could see it was bright and then weak and bright, where it was the brightest point, and you could see that was because the plane of the polarization was horizontal. We're talking about the electrical field. So there's something called the Stokes vector, which describes the polarization character of water completely, of a light beam completely. So I is the intensity. Q is the amount of radiation that's polarized in 0 and 90 degrees, like the laser that we used yesterday. U is the amount of radiation polarized in plus or minus 45 degrees. And then there's something called circular polarization. And you can have circular right polarization and left circular polarization. And there's all of these different parameters that you can derive from all these different polarization parameters. I'm not going to get into, but degree of polarization, these can be very useful. Like if you're like different types of particles have different degree of polarization, et cetera. So it could be used to make the measurements and then derive information about the stuff in the water. So I had to show a Mueller matrix for you guys, but don't get intimidated by it. That's one of the first thing I'm going to say. So on the right, you've got the Stokes vector. We just talked about this. So the total intensity, the polarization, linear polarization, 0 and 90 degrees, linear polarization, 45, plus or minus 45, and then the circular polarization, okay? So you get the incident beam that's fully described by the Stokes parameter. And it goes through a medium, it's scattered, and then you have the scattered beam that's fully described by a Stokes parameter. The only thing the Mueller matrix does is, like this S11 here describes the transformation of that incident intensity to your scattered intensity. So that's your VSF. So that's really easy. So, and these all have angular and spectral character. There's a lot of information here. This S12 describes how linear polarized light, like from that laser pointer you guys were holding, is transformed into unpolarized light in the scattered beam. And then S13 is plus or minus 45, how that's translated into I, and then the V is the circular polarization in I. And you go through, so that's all it is. That's the Mueller matrix. So it's just describing how the incident polarization character of a beam is transformed into the scattered polarization character, polarization character of the scattered beam. So as I mentioned, S11 is your VSF. These other parameters have a lot of information. So S13 and S14 can be used for things like particle orientation. If all your particles are perfectly randomly oriented, they're nominally 0 at all angles. If it's not 0, then you have some degree of particle orientation. You can look at particle non-sphericity. So this is, for instance, is a good estimate of what your bulk kind of, you could call it an aspect ratio. So what the deviation is from non-sphericity. And every element has wavelength and angular dependencies. So there's a tremendous amount of information in here. And, we're starting to, make polarized VSF measurements with the mascot. And Wayne's making those measurements. The LIST VSF can make those measurements now. And there's potentially new sensors, like Wayne was just funded to make a brand spanking new VSF device with polarization character. So there's a lot of information here that very little work has really been done on it. And there's a huge amount of information to tap into. And I think this is really the future of a lot of what we're doing in terms of scattering and ocean optics in the future. If you do make the assumption of randomly oriented particles, then you can forget about a whole lot of these parameters, which really simplifies things. And the S21 and the S11 are typically very, very similar. So it gets very, very much simplified if you make this assumption. I'll just say we have a lot of evidence from a holographic imaging system that we have that there is a significant amount of actual preferential orientation of particles in the ocean, especially when you have shear layers. They orient in those shear layers. So if you can imagine like pencils getting oriented this way, their cross section relative to sunlight coming down and their backscattering is much, much higher than if the pencils were all like trees in a forest. Kind of, yeah, it's good. Yeah, it's kind of looking through the forest this way versus this way. So orientation, I think, is another aspect of just something that has great influence, in my opinion, on ocean optics that really hasn't been looked at very much at all. It's another, one thing to look at. So in 1984, Ken Voss, for his PhD thesis, measured really the first Mueller matrix, and that was on the left there. And then he noted, so you guys, through Darius's and Zhongping's talk, you heard about Rayleigh scattering. This is scattering by very, very, very small particles where you get complete depolarization at 90 degrees, which is what this is shown in this S12 and the S21 here. But you can see there's similar shapes between the two, but you don't get complete depolarization with the measurements that Voss made in the ocean. This is just if you guys are interested in ever making this measurement, you could go back and reference this slide. And what you do is reference the slide and then get Bourne and Huffman 1983, because that's where this table came from. But this shows you how you can make you can resolve all of these different elements of the Mueller matrix by using different analyzers, which are polarization filters over the source and detector. So you just do all these different permutations, all these different combinations, and you can derive the different Mueller matrix parameters. Just wanted to let you guys know how to do that. So with the mascot device, we have put a polarization filter on the front of the device, and it's a rotating filter. So we have the vertical polarization and then the horizontal polarization, but we can also do circular as well. So with this kind of device, we can actually resolve the top row of the Mueller matrix, but we've really focused on what's called degree of linear polarization, which is this S12 normalized to the S11. So these are some measurements that were made in a bunch of different waters. I won't go into the detail. The big thing is that the VSF, as you guys know, looks like this. Degree of linear polarization peaks near 90 degrees, but usually not at 90 degrees. And it's very near 0 at 0 and 180 degrees. But there's a lot of information here that we haven't fully tapped into, and we're trying to work on that right now, actually. And these are some additional measurements that were made in Santa Barbara Channel. What's very interesting, like there's been so little work on this, even though there's so much information with polarization. So up to this point in 2020, there were 3 other measurements that were published of the degree of linear polarization, and 2 were in Russia, and 1 was by Voss in his 1984 thesis. So then we published a paper based on all of our data in 2021 that I'm not going to go into, but it shows degree of linear polarization. It has a simple model to try to interpret it in terms of the particles that are there. I'll just mention that on benchtop systems, degree of linear polarization and other polarization parameters have been measured. This is a very good study by Volton et al. From 1998. They're making measurements in a cuvette, but they made corrections for the reflections I was talking about in the cuvette. So these are very good quality VSFs. Polarization is also used for contrast enhancement. So like this is a picture without polarization. You guys probably know this if you're into photography at all. Polarization filters, I think my son was talking about polarization filter for his camera yesterday. But if you use a circular polarized filter underwater, you dramatically enhance the contrast. So what you're seeing underwater with that contrast is the character of the incident light. And you could actually have a source. The best way to do this is you have a strobe source with circular polarization. You have that circular polarization matched on your detector. You can see very high contrast over very large distances. Yeah. You can also use polarization to enhance contrast in imagery. So if you have 2 polarizations that are in the same plane, on the left, you can kind of see something, but things like jellyfish and a lot of juvenile organisms in the ocean, they're transparent because they're trying to essentially camouflage. But if you cross polarize, you can look at how these tissues of the organisms depolarize the beam, and you get really stark images because you have excellent contrast because it's just all black around the organisms because of the cross polarization. So yeah, this is kind of a next big thing, in my opinion, like interpreting polarized scattering of particles. And there's a lot of information there. There's a lot of information about refractive index composition of the particles, the size distribution of the particles, particle shape, and possibly particle orientation. So, and it can be made, this measurement can be made remotely as well. So there's a lot of potential to learn new stuff, I think, with this kind of technique. Much to be done. And we have polarimeters on PACE now that can make these measurements. So there's going to be, I think, a huge new push, hopefully with funding, to develop new models and new algorithms and new sensors to try to help interpret those data. So when you model scattering, yeah, so Darius talked about this a little bit. I think Zhongping talked about this a little bit. There's a discrete analytical model for Rayleigh scattering that's easy. There's also Lorenz and me came up with exact solutions of Maxwell's equations for homogeneous spheres. That's been extended to coded spheres and also multi-layer spheres. So that's very tractable. There's also this Van der Waals approximation I won't get into. Then there's more advanced modeling that I just wanted to have a slide so you guys could see what's out there, and you could Google it later if you're interested in learning more about it. But geometric optics. So these are particles that aren't spheres. These are more complicated shapes. And for a lot of these models, you can plug in almost any complicated shape you want within reason. They usually have restrictions in terms of size range, refractive index, et cetera. But you can start making VSF simulations. You can model what those VSFs look like for more complex shapes with these models. But they're typically, very intensive in terms of computational time and stuff like that. Finite difference time domain FDTD is something that John's played with a lot, come up with some really nice results that we published in a previous paper. T-matrix, you guys might have heard of that. Anyway, I'm not going to talk any more about that, but if anybody has any questions. So why do the modeling? So you can help qualitatively interpret the measurements that you're making. And if you can really come up with a good explicit model, then you can actually invert it to derive the particle characteristics. This is an example of that. So for non-spherical particles that are very similar to like sediment or sand that's resuspended, so mineral particles, asymmetric hexahedra is a particle type that seems to do a really good job of for simulations. And George Katawar's lab has been making those simulations for atmospheric particles, aerosols, for many years. So we collaborated on redoing those calculations at refractive indices that were pertinent for ocean particles. And so you can do things like this. You can look at size distribution slopes. So assuming, power law distribution for sizes, and then that slope can change. So 4 nominally is quite steep. That's like if everything's dead, you kind of get like 4 is what you get if you have a big boulder and you just start like chomping it up into smaller and smaller bits. You eventually get a size distribution. It's 4. But when you have a lot of growth, especially in larger particles, it tends to flatten that out. You can get down to 3 or even lower. And then so you can look at that as a function of angle, and we can look at that for different refractive indices. And you can come up with these kind of plots where you can look at the degree of linear polarization, that S12, is a function of angle and size distribution slope for the different refractive indices. But in doing all of this, this is a paper in 2021, but there's a follow-on paper that goes into a lot more detail that we've been working on for actually 2 or 3 years after Xiao Zhai left my lab. But yeah, so increasing non-sphericity, there's a lot about the particle population you can glean from these types of measurements in the modeling, but increased non-sphericity lowers the DOLP, degree of linear polarization. Increasing the refractive index lowers the degree of linear polarization, and the size distribution becomes increasingly flat as the degree of linear polarization decreases. And the maximum shifts, there's all these little things that kind of looks like a saddle, like that whole shape. You can play with that shape. There's a lot of information there. So anyway, it's work in progress, but just wanted to show you guys possibilities. I think there's a lot of work for the community to do in polarization. Now I'm going to move to interpretation of an application of the biogeochemical properties. So what can scattering tell you about that? Oh, yeah. Well, yeah, when you're measuring scattering in water, it's always some, finite volume. And there's always tons and tons of particles, even in very small volumes. So it's a bulk refractive index, essentially. Yeah.
Is there a good way to measure that? Or I know you
Yeah.
ways that like get that from the curve.
Yeah. No, it's a great question because like the question is like if we have a model where you can derive refractive index from scattering measurements, and it's used quite often, but you get a refractive index that's a reasonable value, but there's really no way to precisely validate that value. And it's something that we've actually worked on in the past. So certain things like minerals, the best way to do that, how in the lab yesterday, we took the glass rod, we put it in the water, and it was really obvious. Then we put it in the sunflower oil or whatever it was, and it disappeared because the refractive index matched. So what you could do is take a natural sample, and you can start adding some really dense liquid to it. So you're increasing the refractive index of the medium that it's sitting in. So you're getting the medium closer and closer to the refractive index of the particles. So if you could theoretically cycle through a refractive index range of the medium and then measuring attenuation the entire time, you would see a minimum. And that minimum, whatever the refractive index was of the medium at that point, would be the approximate bulk refractive index of that particle population. That's something that we've tried to do over the years, and we've never pulled it off because these dense liquids with high refractive index that you have to add to solution are really nasty. Like they're like carcinogens, and they're incredibly corrosive, very difficult to deal with. So yeah, it's a challenging problem. Yeah, I mean, pretty much, we try to. There's different ways to estimate the refractive index. For instance, one of the things that we're doing is we can come up with an estimate of the refractive index for the bulk population from degree of linear polarization. That is a completely different measurement than backscattering ratio method that was published in 2001. So we get that's exactly what we're doing right now with Xiao Zhai. And if you compare those two and they're pretty close, then you have, yeah. So we're trying to do stuff like that give you kind of indirect validation for refractive index. So it's an excellent question. If you have any good ideas for it, let me know. So for what's commonly done empirically is you can measure an IOP And then you have a concentration or parameter like suspended particulate material, SPM, or particle pigments like chlorophyll, particle size. There's a whole variety of parameters that you can try to solve for. But Beer's law is basically that law that says there's a linear relationship, where you can look into a linear relationship between this inherent optical property and the concentration of the stuff that you're interested in. The problem is, and this, like for instance, like CDOM, this humic fulvic material in water, is a good example. You can go out and measure the absorption of the CDOM and come up relationships between the concentration. You can get the concentration of the CDOM again by actually extracting it in these XAD resins, and then quantifying how much was there. And people have done this, but the problem is that those dissolved and particulate pools of matter vary tremendously throughout the ocean. So you get different linear relations. You do get linear relationships often, but they're different linear relations in different waters. So that's why you really need more complex models. But you know, the fact is the ocean is just really complex. Like you guys have looked under a microscope probably and looked at all the little particles, like just crazy shapes, different colors. I mean, it's very, very, very challenging. And so it's actually much, much more challenging than the atmosphere. And atmospheric optics, like you're looking at ice crystals, those can be easily modeled. They often align perfectly. Like atmospheric optics is a lot just fundamentally more straightforward than it is in the ocean. So yeah, how specifically is an IOP like the attenuation coefficient or the scattering coefficient or the backscattering coefficient directly linked to particles? And the fundamental thing you need to know is that C is directly linked to the cross-sectional area of the particle. And if you have a particle like this, then it's going to be dependent on orientation. Obviously, anything that's non-spherical, which is pretty much every particle that's out there besides bubbles, times the attenuation efficiency. So the efficiency describes if it's 1, that means that 100% of the light that impinged on a particle was scattered. Okay. Now, as you can see here, this is efficiency as a function of size, essentially. So rho is size, but it's normalized to the wavelength of light. But you can see that the efficiency tends to oscillate and eventually reach an asymptote of 2. So that means that if 1 means 100% of the light impinging on a particle is scattered, and we're actually getting it to reach this asymptote of 2, do you guys have any idea why you get twice as much scattering than what's actually impinging on the particle? If you think about the 3 different scattering processes that we talked about earlier, they're reflection, refraction, and diffraction. So what happens is that you're getting diffraction around the particle. So for larger particles, about half of the light scattering, the total light scattering, is actually coming from diffraction. That's how you can get it to 2. And but these oscillations are due to constructive and deconstructive interference. Anyway, so if you have this attenuation efficiency and you have, like, say you have microspherical beads, they're all 2-micron beads, you can calculate exactly what the cross-sectional area is of that, and then you know their size on this chart. You can look up what the scattering efficiency or the attenuation efficiency is, and if you know how many of those particles are in there, you can directly calculate exactly what C should be. So that's the link between particles, the size, and the type of particle. The attenuation efficiency is mostly a function of size. So with a population of particles, you've got basically the attenuation efficiency here for the particles, and you can define it for each size class. And then you've got the size distribution here, which is represented by FR. So this is just basically how you weight the contribution from different sizes. And then this is for spheres. So pi r squared is the area, cross-sectional area of a sphere. Yeah, and what's interesting for very, very small particles, you see that the attenuation efficiency is increasing almost linearly with the size of the particle. So if you plug that into this into this equation, then you really have, so your QC is proportional to V or to R. Actually, this will work. So if you plug that into here, then you get, because you already have an R squared in the equation, you actually get a D to the third. So it's showing you that for very small particles, the attenuation coefficient is proportional to the volume, the total volume of the particles. And then when you get to large enough particles where it's oscillating around 2, really 2 is a good approximation, and just QC is equal to 2, and you're left with the R squared in the equation. So it's proportional to the length scale of the particle squared, so it's more proportional to total surface area or total cross-sectional area. This, in most cases, C is going to be very closely proportional to the total cross-sectional area of the particle population. But if you have a lot of small particles, you can start to skew that. Does that make sense? This is pretty important because this is really the link between like what attenuation is and then like what like that Arizona road dust that we had in the tank yesterday and shining that laser through, and you see that attenuation really obviously in the water column. This is linking it back. Like you can actually use that attenuation to calculate, you know, the attenuation or really the size distribution, or it gets some estimate of the size. I'm just saying there's information there, and that's what this is, the link to the information of those particles and their size and their attenuation efficiency. So you have widely varying size distributions in particle bulk refractive index are the main reasons why people have, like, you can collect all the particles onto a filter, you can weigh that before and after, and so then you get your suspended particulate matter weight, and you can compare that to C. A lot of people have looked at this, and you get linear relationships in certain times and places, but it varies a lot. So this is an example. This is actually the first example of when it was ever done, 1977, with one of the first transmissometers. This was out of Ron Zonnefeld's lab with a postdoc, I think with a PhD student, Peterson. But you can see you got, so this is TSM versus C, and you get some linear relationships, but these slopes on these linear relationships are different in each of the different regions. You can also use it to look, here's backscattering versus SPM, which is the same thing. It's TSM, suspended particulate matter. And these are 4 different instruments. And the one that actually did best was the backscattering measurement. But empirically, you get linear relationships, but they do vary in different locations is the point. Yeah, and this is a table of just a bunch of published data from TSM, CP, as well as particular organic carbon. And there's a wide range of slopes that you get. So yeah, Zhangping showed this. I'll just show it really briefly. There's also an analytical inversion we developed to solve for the bulk particulate refractive index. This is the simple relationship here. So refractive index is a function of the backscattering ratio. And it's a pretty tight relationship, but if you include the slope of attenuation spectrum, which I'm not going to get into, you can do quite a bit better, actually. So that's that full equation at the top here. But in any case, you could see this intuitively when we were looking at the glass beads yesterday, or the carbohydrate beads, you know, when they were still dry and you put the light, those lasers of light into the beads, very, very bright scattering backward. And then when you put it in the beads that were filled with water, much, much lower refractive index, there was very, very little backscattered light from those. So the higher refractive index, you're going to get more backscattered light. This just quantified that in a model that we could use to invert it to derive refractive index. We also did some other, this is another example of inversion of a full VSF. So this was specifically looking in a surf zone. And here's actually, this was a video, but it didn't work. And it's off Scripps Pier. We have the scattering measurements in the water and shows this wave crashing over it, which is really nice. Use your imagination for that. But what's nice about this is we assume they're basically a background particle population, and then you had bubbles injected from the wave breaking. Again, bubbles are like the easiest thing to try to understand their scattering because they're spheres. So we can use Lorentz-Mean theory for that. So that's what this is. I mean, this is relative bubble size, and then this is angle. And this shows very nicely that mid-angle enhancement that you can see in our direct measurements. And then we had sediment-laden water come through much, much higher backscattering relative to back. So again, this is a log scale, so it's much higher relative backscattering relative to the background. So those are the two populations we were looking at their dynamics relative to the background. And we could actually derive bubble concentrations with this inversion. And at the same time, we had David Farmer and Helen Schertsky had an acoustic resonator that could look at bubbles, and they put it on the same package. So we were looking at basically the same water together. And yeah, it's one thing to come up with an algorithm like refractive index and not be able to validate it. But in this case, we could essentially validate it with this whole other measurement technique. So this was really cool. But you could see that the peaks between the bubbles and their measurements lined up really well. And this might be my last slide, but just to go over kind of the relevance of VSF to ocean color, you guys haven't really been introduced, but maybe you already have some background in it, but you haven't really been introduced into the relationships between the inherent optical properties and remote sensing reflectance. I know Zhangping's going to get into that later with talking about inversion models and stuff like that, but this is really the essence of those inversion models, where you have remote sensing reflectance is the upwelling radiance normalized to the downwelling irradiance from the sun, and that's approximately proportional to BB over A plus BB. And so you have this is the water leaving radiance, and then you get, so the water leaving radiance, like I was saying, you have the sun and you have your imager somewhere, and that creates some in-water angle, which is shown here. And that there's a what's called a BRDF correction to then normalize that, so we have the same geometry across an entire image at any time and place. So it's a very important correction. That's controlled by the BRDF. So that's one of a very important thing that the VSF is needed for in ocean color. Also, this proportionality between BB over A plus BB and remote sensing reflectance is dependent on the VSF, and you have to make some assumptions about the VSF in the algorithms. And then obviously the backscattering coefficient is directly derived from the VSF. So my summary slide, as I've been mentioning the whole way, there's a lot to do. So for spectral scattering, the hyperspectral BB, we're just starting to make those measurements now. It's very, very exciting. We're starting to see consistent deviations from just power law, simple power law assumptions that we've made spectrally for many, many years. So exciting topic to get into. The phase function shape and how that varies spectrally. And then, as I mentioned, anomalous dispersion. So how the absorption peaks affect hyperspectral backscattering is also really, really, and I think, you know, as Zhangping will talk about in the inversions for ocean color, you know, you have to make assumptions about the spectral shape of BB. You have to make assumptions about the absorption, and that interplay in BB over A that's proportional to the reflectance is really important. And this effect actually could be something that's more important than we realize right now. Beta 180, as I mentioned, especially with the onset of new LiDAR sensors measuring backscattering in the kind of retroreflective direction, it's going to be really important. Scattering by non-spherical complex particle populations, that's pretty much what's in the ocean, and very important. Oriented particles, again, I think that's important. When we have evidence to show that that is, you know, happens in the ocean quite a bit. Anything to do with polarization, especially with PACE and the polarimeters, it's an exciting time, really, for looking at polarized scattering and interpreting that. And the remote algorithms from space, including both ocean color and polarimetry, that explicitly use the VSF, it's kind of bringing it all together, using ocean color with the polarimetry.